a WikiVidi Documentaries production. Don't forget to like and subscribe. Enjoy. Riemann hypothesis. In mathematics, the Riemann hypothesis is a conjecture that the Riemann zeta function has its zeros only at the negative even integers and complex numbers with real part. It was proposed by, after whom it is named. The name is also used for some closely related analogues, such as the Riemann hypothesis for curves over finite fields. The Riemann hypothesis implies results about the distribution of prime numbers. Along with suitable generalizations, some mathematicians consider it the most important unresolved problem in pure mathematics. The Riemann hypothesis and some of its generalizations, along with Goldbach's conjecture and the twin prime conjecture, comprise Hilbert's eighth problem in David Hilbert's list of 23 unsolved problems. It is also one of the Clay Mathematics Institute's Millennium Prize problems. The Riemann zeta function zeta is a function whose argument s may be any complex number other than 1, and whose values are also complex. It has zeros at the negative even integers. That is, zeta 0 when s is 1 of -2, -4, -6. These are called its trivial zeros. However, the negative even integers are not the only values for which the zeta function is 0. The other ones are called non-trivial zeros. The Riemann hypothesis is concerned with the locations of these non-trivial zeros, and states that, thus, if the hypothesis is correct, all the non-trivial zeros lie on the critical line consisting of the complex numbers where t is a real number and I is the imaginary unit. There are several non-technical books on the Riemann hypothesis, such as the books, and give mathematical introductions, while, and are advanced monographs. Riemann zeta function. The Riemann zeta function is defined for complex s with real part greater than 1 by the absolutely convergent infinite series \zeta\sum _caret \inft \frac plus \frac plus Leonhard Euler already considered this series in the 1730s for real values of s, in conjunction with his solution to the Basel problem. He also proved that it equals the Euler product \zeta \prod _frac c dot \frac c dot \frac c dot \frac c dot \frac dots where the infinite product extends over all prime numbers. Page the Riemann hypothesis discusses zeros outside the region of convergence of this series and Euler product. To make sense of the hypothesis, it is necessary to analytically continue the function to give it a definition that is valid for all complex s. This can be done by expressing it in terms of the Dirichlet function as follows. If the real part of s is greater than 1, then the zeta function satisfies \left \zeta \sum _caret \inft \frac plus \frac dots. However, the series on the right converges not just when the real part of s is greater than 1, but more generally whenever s has positive real part. Thus, this alternative series extends the zeta function from to the larger domain, excluding the zeros s1 plus 2 \pi and /lane of 1 and 2 halves to the power of s. The zeta function can be extended to these values as well, by taking limits, giving a finite value for all values of s with positive real part except for a simple pole at s1. In the strip, the zeta function satisfies the functional equation \zeta 2 to the power of s \pi caret sin left gamma zeta. One may then define zeta for all remaining non-zero complex numbers s by assuming that this equation holds outside the strip as well, and letting zeta equal the right-hand side of the equation whenever s has non-positive real part. If s is a negative even integer, then zeta 0, because the factor sin vanishes. These are the trivial zeros of the zeta function. The values eta minus half is not determined by the functional equation, but is the limiting value of z2 as s approaches 0. The functional equation also implies that the zeta function has no zeros with negative real part other than the trivial zeros, so all non-trivial zeros lie in the critical strip where S has real part between 0 and 1. Origin. Riemann's original motivation for studying the zeta function and its zeros was their occurrence in his explicit formula for the number of primes pi less than a given number x, which he published in his 1859 paper on the number of primes less than a given magnitude. His formula was given in terms of the related function begin /pi and /pi plus /tfrac /pi plus /tfrac /pi plus /tfrac /pi and plus /tfrac /pi plus /tfrac /pi plus dots /end, which counts the primes and prime powers up to x, counting a prime power Pn as 1/n of a prime. The number of primes can be recovered from this function by using the Mobius inversion formula: begin /pi and sum underscore caret /frac /pi and /pi frac /pi frac /pi plus frac /pi dots /end, where mu is the Mobius function. Riemann's formula is then begin /pi underscore 0 and operator name sum underscore rho operator name log plus int underscore x caret inft frac end, where the sum is over the non-trivial zeros of the zeta function, and where pi 0 is a slightly modified version of pi that replaces its value at its points of discontinuity by the average of its upper and lower limits. /pi underscore 0 lim underscore frac 2. The summation in Riemann's formula is not absolutely convergent, but may be evaluated by taking the zeros row in order of the absolute value of their imaginary part. The function Li occurring in the first term is the logarithmic integral function given by the Cauchy principal value of the divergent integral operator name int underscore 0 to the power of x frac. The terms Li involving the zeros of the zeta function need some care in their definition, as Li has branch points at 0 and 1, and are defined by analytic continuation in the complex variable rho in the region ρ greater than 0, i.e., they should be considered as. The other terms also correspond to zeros. The dominant term Li comes from the pole at S1, considered as a zero of multiplicity -1, and the remaining small terms come from the trivial zeros. For some graphs of the sums of the first few terms of this series, see or. This formula says that the zeros of the Riemann zeta function control the oscillations of primes around their expected positions. Riemann knew that the non-trivial zeros of the zeta function were symmetrically distributed about the line, and he knew that all of its non-trivial zeros must lie in the range. He checked that a few of the zeros lay on the critical line with real part half and suggested that they all do. This is the Riemann hypothesis. Distribution of prime numbers. Riemann's explicit formula for the number of primes less than a given number in terms of a sum over the zeros of the Riemann zeta function says that the magnitude of the oscillations of primes around their expected position is controlled by the real parts of the zeros of the zeta function. In particular, the error term in the prime number theorem is closely related to the position of the zeros. For example, if beta is the upper bound of the real parts of the zeros, then the difference pi Li has the error bound O. It is already known that half less than or equal to beta less than or equal to 1. Von Koch proved that the Riemann hypothesis implies the best possible bound for the error of the prime number theorem. A precise version of Koch's result, due to, says that the Riemann hypothesis implies vertical bar /pi operator name vertical bar, where pi is the prime counting function and log is the natural logarithm of x. Also showed that the Riemann hypothesis implies vertical bar /psi x vertical bar, where psi is Chebyshev's second function. Proved that the Riemann hypothesis implies there is a prime p satisfying /frac /sqrt log x for all x check 2. This is an explicit version of a theorem of Kramer. Growth of arithmetic functions. The Riemann hypothesis implies strong bounds on the growth of many other arithmetic functions, in addition to the primes counting function above. One example involves the Mobius function mu. The statement that the equation \frac \sum _caret \infinity \frac is valid for every s with real part greater than half, with the sum on the right-hand side converging, is equivalent to the Riemann hypothesis. From this we can also conclude that if the Mertens function is defined by m \sum _mu, then the claim that mo for every positive epsilon is equivalent to the Riemann hypothesis. The determinant of the order n Redheffer matrix is equal to m, so the Riemann hypothesis can also be stated as a condition on the growth of these determinants. The Riemann hypothesis puts a rather tight bound on the growth of m, since disproved the slightly stronger Mertens conjecture, vertical bar m vertical bar \la sqrtx. The Riemann hypothesis is equivalent to many other conjectures about the rate of growth of other arithmetic functions aside from mu. A typical example is Robin's theorem, which states that if sigma is the divisor function given by \sigma \sum _d, then \sigma for all n greater than 5040 if and only if the Riemann hypothesis is true, where gamma is the Euler-Mascheroni constant. Another example was found by Jerome Fresnel, and extended by Landor. The Riemann hypothesis is equivalent to several statements showing that the terms of the Féré sequence are fairly regular. One such equivalence is as follows: if Fn is the Féré sequence of order n, beginning with 1/n and up to 1, then the claim that for all epsilon greater than 0, \sum _caret m vertical bar f _ n \frac vertical bar o is equivalent to the Riemann hypothesis. Here, m \sum _caret n \phi is the number of terms in the Féré sequence of order n. For an example from group theory, if G is Landor's function given by the maximal order of elements of the symmetric group Sn of degree n, then showed that the Riemann hypothesis is equivalent to the bound \log G for all sufficiently large n. Lindelöf hypothesis and growth of the zeta function. The Riemann hypothesis has various weaker consequences as well. One is the Lindelöf hypothesis on the rate of growth of the zeta function on the critical line, which says that, for any epsilon greater than 0, \zeta left o, as t. The Riemann hypothesis also implies quite sharp bounds for the growth rate of the zeta function in other regions of the critical strip. For example, it implies that e⁻gamma \la lim sup _frac {la2 e⁻gamma phrase \gamma \la lim sup _frac {la phrase gamma, so the growth rate of zeta and its inverse would be known up to a factor of 2. Large prime gap conjecture. The prime number theorem implies that on average, the gap between the prime p and its successor is log page. However, some gaps between primes may be much larger than the average. Kramer proved that, assuming the Riemann hypothesis, every gap is O. This is a case in which even the best bound that can be proved using the Riemann hypothesis is far weaker than what seems true. Kramer's conjecture implies that every gap is O2, which, while larger than the average gap, is far smaller than the bound implied by the Riemann hypothesis. Numerical evidence supports Kramer's conjecture. Criteria equivalent to the Riemann hypothesis. Many statements equivalent to the Riemann hypothesis have been found, though so far none of them have led to much progress in proving it. Some typical examples are as follows. The Riesz criterion was given by, to the effect that the bound \sum _caret \infinity \frac o left holds for all epsilon greater than 0 if and only if the Riemann hypothesis holds, proved that the Riemann hypothesis is true if and only if the space of functions of the form f \sum _caret North Carolina _new \rho left, where O is the fractional part of z, and \sum_North Carolina _new /theta _new 0 is dense in the Hilbert space L2 of square integrable functions on the unit interval. Extended this by showing that the zeta function has no zeros with real part greater than 1/p if and only if this function space is dense in LP. Showed that the Riemann hypothesis is true if and only if the integral equation \int_caret\inft\frac dz0 has no non-trivial bounded solutions \phi for half. Weil's criterion is the statement that the positivity of a certain function is equivalent to the Riemann hypothesis. Related is Lie criterion. A statement that the positivity of a certain sequence of numbers is equivalent to the Riemann hypothesis. Proved that the Riemann hypothesis is equivalent to the statement that \zeta, the derivative of \zeta, has no zeros in the strip 0. That \zeta has only simple zeros on the critical line is equivalent to its derivative having no zeros on the critical line. The Fairy sequence provides two equivalences, due to Jerome Fresnel and Edmond Landau in 1924. Consequences of the generalized Riemann hypothesis. Several applications use the generalized Riemann hypothesis for Dirichlet series or zeta functions of number fields rather than just the Riemann hypothesis. Many basic properties of the Riemann zeta function can easily be generalized to all Dirichlet series. So it is plausible that a method that proves the Riemann hypothesis for the Riemann zeta function would also work for the generalized Riemann hypothesis for Dirichlet functions. Several results first proved using the generalized Riemann hypothesis were later given unconditional proofs without using it, though these were usually much harder. Many of the consequences on the following list are taken from \lim_\sum_caret x to the power of p plus \inft, which says that in some sense primes 3 mod 4 are more common than primes 1 mod 4. Excluded middle. Some consequences of the RH are also consequences of its negation, and are thus theorems. In their discussion of the Hecker, Daring, Mordell, Heilbronn theorem, say the method of proof here is truly amazing. If the generalized Riemann hypothesis is true, then the theorem is true. If the generalized Riemann hypothesis is false, then the theorem is true. Thus, the theorem is true. Care should be taken to understand what is meant by saying the generalized Riemann hypothesis is false. One should specify exactly which class of Dirichlet series has a counterexample. Littlewood's theorem. This concerns the sign of the error in the prime number theorem. It has been computed that pi23, and no value of x is known for which pi greater than Lie. See this table. In 1914 Littlewood proved that there are arbitrarily large values of x for which \pi \operator name plus \frac 13 \frac log x, and that there are also arbitrarily large values of x for which \pi thus the difference pi minus Lie changes sign infinitely many times. Skews number is an estimate of the value of x corresponding to the first sign change. Littlewood's proof is divided into two cases. The RH is assumed false, and the RH is assumed true. Gauss's class number conjecture. This is the conjecture that there are only a finite number of imaginary quadratic fields with a given class number. One way to prove it would be to show that as the discriminant d minus the class number h. The following sequence of theorems involving the Riemann hypothesis is described in theorem. Let dh greater than c \frac. Theorem. If the RH is false then h greater than 1 if vertical bar d vertical bar is sufficiently large. Theorem. If the RH is false then h is d minus. Theorem. If the generalized RH is false for the L function of some imaginary quadratic Dirichlet character then h is d minus. In 1935, Carl Siegel later strengthened the result without using RH or GRH in any way. Growth of Euler's totient. In 1983 J. L. Nicholas proved that \varphi for infinitely many n, where phi is Euler's totient function and gamma is Euler's constant. Riemann remarks that the method of proof is interesting. in that the inequality is shown first under the assumption that the Riemann hypothesis is true, secondly under the contrary assumption. Brought to you by WikiVidi Documentaries. Would you like to know more?